Hi, in this video we're going to talk about the concept of heterogeneous equilibrium. So take for example, if you have a reaction, let's say H2 plus O2 gives you H2O, and if you balance this, it would be 2H2 plus O2 gives you 2H2O. Now notice carefully, in this reaction, everything is in the same phase. So you have gas, gas, and gas, okay? This would be an example of homogeneous equilibrium. Homogeneous because everything is in the same phase. Now in the case of heterogeneous equilibria, let's say you have a reaction carbon plus oxygen, and that gives you carbon dioxide. That's completely balanced, by the way. Notice carefully, the carbon out here is in the solid phase, while the oxygen and the carbon dioxide gas, they're both in the gaseous phase. Therefore, if you take a look at all the phases together, that's a case of heterogeneous equilibria. Okay, so now if we talk about the equilibrium, so let's say the reaction is going forward and backward. In this case, it would be homogeneous. In that case, it would be heterogeneous. So for the homogeneous reaction, if I had to write the equilibrium constant for this reaction, I'm going to go ahead and erase this part so I can write the equilibrium constant. That would be Kc is equal to the product, concentration of the product raised to the coefficient over the concentration of the reactant raised to the coefficient times the concentration of, so H2 raised to the coefficient times oxygen raised to 1. Now this could also be expressed as Kp is equal to the partial pressure of water squared, so raised to the coefficient, over the partial pressure of H2 raised to 2 times the partial pressure of oxygen. Okay, and then of course you should know how to relate Kc and Kp. There's a relationship for that. But if you have to express something out here for the heterogeneous case, then if you have a solid, it will not appear in the equilibrium constant. So Kc for this would be written as simply the gaseous form raised to the coefficient of 1 over oxygen raised to the coefficient of 1. If you expressed it in terms of partial pressures, Kp would be equal to partial pressure of carbon dioxide over partial pressure of oxygen. Carbon does not appear. So, as a side note, what does not appear? Anything in the solid form or pure liquids. So, if it's a solid or pure liquid. So, pure liquids would be, that means out here in parentheses, you'll see a little L. It'll show up like that. If it's a solid, it'll show up with an S. So if you see an S or an L, that means it will not appear in the expression for Kc or Kp. Okay? Now, so what will appear in the expression? So what will appear is anything that appears as a G, so gaseous form, just as we saw, or a Q, aqueous form. Because these two, the concentrations can vary. Gases can change in concentration when you look at partial pressures. Aqueous solutions can also change in concentration. So when the concentrations are variable, then they should show up in the expression for equilibrium constant. When the concentrations are not variable, so out here, the concentration is essentially a constant, it doesn't make sense to include that in the equilibrium expression. Another thing to keep in mind is whenever you derive the actual value of the equilibrium constant, the value is always going to be unitless. Okay, so whether it's Kp or whether it's Kc, there are no units. Okay, so this is a unitless expression. Okay, let's do one example and wrap this up. Take a look at this reaction. Out here you have one of the reactants is a gas, another one is a liquid, and then you have the products both in aqueous. So if you had to write the equilibrium constant for this, it would be K is equal to, remember, we don't include liquids, so it's only going to be the product, these two products, and then this reactant, the carbon dioxide. So the value of equilibrium constant, Kc, would be equal to H plus, concentration of H plus, times the concentration of HCO3 minus, and the whole thing is divided by the concentration of carbon dioxide. And if the values of these were given, then that would be unitless. Now, one thing to note is, oftentimes when you're solving a problem, all of these will be given at a particular temperature. That's because the equilibrium constant changes with temperature. So usually the equilibrium constant, let's say the value for this came out to be 0.025, no units, but you will need to specify the temperature. So let's say this was run at 25 degrees Celsius. So then you would write at 25 degrees Celsius.